So in this lecture, we're going to talk about inverse Laplace transforms, but I'd like to start out by recalling what we did in the previous lecture. So last time, we introduced the Laplace transform. Okay, and we use a symbol capital L for the Laplace transform. And let's just recall how it's defined. We input a function of t, and then the output is a function of the variable s. So to be precise, it's this integral, 0 to infinity e to the negative st of our function f of t dt. It's an integral with respect to t, so the t actually goes away when we plug in these bounds, and we're left with a function of s. And recall we also denote this by just capital F of s. So capital F of s is the Laplace transform of little f of t. And so the main question today is actually going to be, so here's a question. Given a function capital F of s, okay, what is the function little f of t such that the Laplace transform of f of t is our given function, f of s. Okay? So we want to sort of work this backwards. And in this situation, we call this little f of t the inverse Laplace transform. The inverse Laplace transform of capital F of s. And we write it like this. L inverse, so L negative 1 power, meaning denoting the inverse Laplace transform. So for the inverse Laplace transform, we input the function of s, and we get a function of t. Okay. And so the nice thing about this is that this f of t here is essentially uniquely determined by this capital F of s. There are a few subtleties, so this could have different values at a discrete set of points, for example, than the one we started with. But this f of t is essentially uniquely determined, and so this is a well-defined concept. And what we're going to do today is discuss how to compute this. So how do we compute inverse Laplace transforms? And it's not so easy. You can't just do this integral backwards. And it turns out there is a formula involving an integral for calculating inverse Laplace transforms. But it's pretty complicated. It actually involves complex contour integrals. So contour integrals in the complex plane. And so what we're actually going to do is, so we will be using a table to compute inverse Laplace transforms. That sounds boring, but it actually turns out to be pretty fun. So you'll see that it's not so easy. We'll actually be using this table that we started last time. So the first thing I would like to mention is that let's call this a note. So just like capital L inverse, the inverse Laplace transform is a linear operator. is a linear operator. Yeah, I should say just like capital L is. Meaning a Laplace transform of a sum of two functions of S. You can take the inverse Laplace transform of both parts separately and then add them. And you can pull out constants as well. So let's see why this is true. Shouldn't be too hard. So what if we take the inverse Laplace transform of C1 times capital F of S plus C2 times capital G of S, some other function. Okay. Well, here's what I'm going to do. I'm going to try to use the fact that L is a linear operator. So I'm actually going to write capital F of S as L of little f of t. Okay, so where this little f of t is the inverse Laplace transform of capital F of S. And then plus C2 L of little g of t. I need another parentheses there. Yep. Okay, and then next, I'm going to use the fact that the Laplace transform is linear. So I can write that inside bit as actually L of C1 f of t plus C2 g of t. I don't need that parentheses there, but that's okay. And another one. Okay. Okay, well, what is this here? I'm taking the Laplace transform, then I'm immediately taking its inverse. So what should this be? I should just get this function here back. C1 f of t plus C2 g of t. And what is f of t? F of t is the inverse Laplace transform of capital F of S. And similarly for g of t, it's the inverse Laplace transform of capital G of S. And so look at what we just showed, right? The inverse Laplace transform of this is C1 plus the inverse Laplace transform of F plus C2 times the inverse Laplace transform of G. So in other words, this is a linear operator. And this is the proof here. So this is, why is it a linear operator? Because of this. Okay, and so that will be useful to us. And for the rest of this lecture, I'd just like to do a bunch of examples showing some of the, say, the difficulties that can arise. Okay. So, first example. Let's do the inverse Laplace transform of 1 over s squared plus 3. Let's just recall what this means, right? So this means what is, some function f of t such that L of f of t is this 1 over s squared plus 3, right? That's what we mean by this notation. Okay. And again, I said we're going to use our table. So let's look at our table. And we want to see basically if this looks like anything in the table. Well, it doesn't exactly. So it's similar to these ones right here, sine and cosine. However, the cosine has an s in the numerator, and we don't have that. This one has the number a in the numerator, so let's make note of this formula. So the Laplace transform of sine at is a over s squared plus a squared. And we'll go back here. Okay, can I just use this formula? Well, what would my a be? That 3, I want to interpret as a squared. Okay, so my a is square root of 3. The only problem is I need that a to be in the numerator as well, or I can't use this formula. But that's easy to do. That's easy to arrange. And here's how you do it. So I'll write this as s squared plus, just to make it very clear, it's the square root of 3 squared. So that's my a squared. And now I want a to be here, so I'm just going to put it in. But I can't change the problem. So I start with a 1 there. So do you see what I have to do in order to keep it the same problem? I just multiply by a 1 over square root of 3. Okay. So this is inverse Laplace transform of this. And now this is exactly in this form. So, and notice I'm just multiplying by a constant, but this is a linear operator. So it's just going to be 1 over square root of 3 times sine of at. So sine of square root of 3t. Great. So we did our first inverse Laplace transform. Let's do another example. Okay. How about, let's do 1 over s minus 2 to the 4th power. Okay. All right. So does this one ring a bell? Does this look familiar? Let's look at our table. Okay, so it's actually not going to be these because we have an extra plus b squared there. Right? We don't have that here. I suppose you could say b is going to be 0, but then that would kill off the numerator as well. So do we see anything that looks more like this? Well, how about this one? N factorial over s minus a to the n plus 1. So let me copy that down. So that is L of t to the n e to the at equals n factorial over s minus a to the n plus 1. Notice I'm always starting in the second column, right? Because we have the Laplace transform. We want to find the function that gives that as the Laplace transform. Okay. And so can we view this as this right here? Well, sure, right? So a is going to be number 2. What is n here? N plus 1 is 4, which means n is 3. In my numerator, I have an n factorial. Well, what is 3 factorial? 3 factorial is 3 times 2 times 1, which is 6. So I want a 6 in the numerator in order to use this formula. So we know what to do. Let's just, I can even take it out right now. So I'll multiply by 1 over 6 in order to get a 6 in the numerator. S minus 2, 4. Now we just have to be careful about all of the, what is what, which is n, which is a, etc. No, that 6 is 3 factorial right there. Right, so n is 3. So my answer is going to be this 1/6 times t to the 3, right, times e to the 2t. Okay. So, not so bad so far. Let's do a harder example. Okay. How about... okay, so actually I'm going to choose these next two examples to illustrate two typical ideas that are used when finding inverse Laplace transforms. So the first idea is going to be actually completing a square. So let's do s over s squared plus 6s plus 10. Okay, we want the inverse Laplace transform. Again, we can look at our table here. Put them both in the screen. This doesn't quite look like anything in the table. All right, I see a lot of s squareds in the denominator, but I don't see an s anywhere. And that's because we haven't completed a square here. Okay, so when we have a quadratic equation in the denominator, we can always complete the square. And let's just recall how that works. So completing the square just write it. Completing the square. We have a quadratic. You can always write that in this form. S plus or minus something squared, and then plus or minus some number. Okay, so I have some number there and some number here. And it's not hard to find what numbers those have to be. So notice that this number, when I square this, I'm going to get this here. And this is actually going to be twice that number. So this should be 3. Okay. Just to make this super clear, when I write out s plus 3 times s plus 3, I'm going to get an s squared plus 3s plus another 3s, right? So I get 6s. So this is twice that number there. But I also get a plus 9, right? I have a plus 9. But I see that there's actually a plus 10, which means that this has to be a 1. Okay, so that's completing a square. You've surely seen this idea before, but I just wanted to remind you how it works. And so why is this going to be useful? Well, let's take a look. So s plus 3 squared plus 1 is a way we can rewrite the denominator. And let's go back to our table here. It looks now very similar to, well, these two. Notice I have an s in the denominator, or the numerator actually. So that rules out this one here, because I don't have an s there. I want to use this formula here, e to the at cosine bt. Let me copy down that formula. But you might notice that one still looks a little bit different. So we're going to have to do something else. Okay. We just have an s in the numerator. We don't have an s minus a. What would a be in this example? It would be negative 3. All right, so let's just write out what a would be. So a would be negative 3. B would be, well, 1 squared. Sorry, this 1 is b squared. Right, so b has to be 1. But I do not have an s minus 3 in the numerator. So are we out of luck? Well, the answer is no, because I can just write one in. Or sorry, an s plus 3. But I can't change the problem, right? So here's what I'm going to do. I'm actually going to write this as s plus 3 minus 3. This is a typical idea. And then I'm going to break this fraction apart. So I'll keep this s plus 3 of s plus 3 over s plus 3 squared plus 1. And then I have minus 3 over s plus 3. We're going to say plus negative 3, right, over s plus 3 squared plus 1. This looks exactly now like this formula. However, we're actually left with this bit, but that's okay because you'll notice that we can actually use this formula here now. Okay. So when I have a constant in the numerator, I can use this, the e to the at sine bt formula. But notice that we need a 1, not a negative 3. So what is this going to become? Well, I haven't been writing down all these L inverse, but let's now take the inverse Laplace transform. This one is just going to be exactly e to the at, right? So a is what? A is a negative 3, right? It's s minus a, s minus negative 3, times cosine 1t. And then I want a 1 here instead of a minus 3. Right? There's a b in the numerator, which is 1. So I'll just take that minus 3 out. So I have minus 3 times e to the minus 3t sine t. Okay, great. So that's an example of how completing a square can be used. And you should also take note of this idea where we want an s plus 3 in the numerator, so we just write in s plus 3, but then we have to subtract 3. And then we break this apart actually into two fractions. So it looks like we're making the problem more complicated, but both of these are actually things that are known Laplace transforms of functions. You might also notice that this is starting to look like a solution perhaps to a second order linear differential equation. And so I'm going to see the connection in the next lecture. Okay, and let's do one more example. So this is completing a square. Another typical idea for finding inverse Laplace transforms is a partial fractions technique. So let's do an example where that will be useful. So we'll do 8s squared minus 6s plus 27. These numbers look really nasty, but they're chosen actually to make it work out nicer. And then the denominator is s times s squared plus 9. Okay, so this definitely doesn't look like anything in the table. I can tell you that for sure. So the first step is actually going to be to try to break this down into smaller pieces. Also, I just want to note in this previous problem we actually used linearity here, right? Because inverse Laplace transform of a sum, we can just take the inverse Laplace transform of both pieces, and we use linearity also to bring out the minus 3. Okay. So yeah, again, the idea is to take this this fraction here, this rational function, and break it down into smaller pieces. So we're going to view this as the sum of two smaller fractions. So potentially this could have come from adding a fraction with a denominator of s and one with a denominator of s squared plus 9. Okay, and then this would be the common denominator. And we want to figure out what the numerators should be in order to get this. So here's what I'll do. I'll guess that, well, I don't have to guess anything yet, but I'll just say, suppose we had some constant there, a. And then for this one, we actually need to assume that the numerator is a linear function. And that's because we have a quadratic equation here. And so if we just put b over s squared plus 9 and then we added those together, it turns out you won't always be able to get anything you want in the numerator. And so we always choose the form of this function in the numerator to have degree 1 less than the denominator. Okay, so if this were a cubic, I would have to write a quadratic, bs squared plus cs plus d. Okay, and this one I could get away with a constant just because we had a linear function here. So I just need a constant a. Okay. Well, now what do we do? Well, let's try adding these together. Okay, so this should be blue. Okay, well, our common denominator is going to be s times s squared plus 9. So this one here I need to multiply by s squared plus 9 over s squared plus 9. This is our first example of partial fractions, so I'll try to write out everything very explicitly. S squared plus 9. We have our a there. And then this one, I need to multiply by s over s. So I have a bs plus c times s, okay? Now when we simplify this, so we just add the two fractions now. So the denominator is going to be s times s squared plus 9, and we add the numerators. So we get as squared plus 9a plus bs squared plus cs. Okay. And I want this to equal this, right? So here's what I want. I want my numerator to actually be 8s squared minus 6s plus 27 over this denominator. And how will I do that? Well, I have s squared terms, I have s terms, and I have constant terms. Okay, so here are my s squared terms. The s squared terms have to be the same on both sides. Right? There's no way one of these terms, like a cs, could have contributed to that 8s squared. They're unlike terms. So basically just setting these equal as squared plus bs squared equals 8s squared. So 8 has to be a plus b. Okay. Then let's use another color maybe. So then I have s terms. So there's minus 6s. Here I have cs, which means minus 6 has to be c. That was easy. So we got c automatically, and that'll often happen. Don't be too intimidated by partial fractions, because it seems like we're going to get 3 equations, and we'll have a system of 3 equations. But often you'll just be able to figure out right away what some of the variables are, or what some of these a, b, and c are. And then the constant terms on both sides, I have a 27 and a 9a. So 27 just has to equal 9a. Which tells me that a equals 3. So I have 2 out of 3 already. And then a plus b is 8, which means b has to equal 5. Okay. What does that mean? It means that I can actually write this function as this, right? So I write it down one more time. Over this. This is actually equal to a over s, so 3 over s, plus bs plus c over s squared plus 9. 5s minus 6 over s squared plus 9. Okay. And now let's see what we have. So notice we ended up with much simpler pieces here. This is the same function as that, but it's easier to work with. And we already see that this bit here is going to just become a 3, right? Because the Laplace transform of 1 is 1 over s. We have 3 over s, so its inverse Laplace transform will be 3. And then this part here looks like the sine and the cosine. But we actually have to split this up into 2 parts. Can you see that? Because we want just the s over s squared plus a squared, and then we want a over s squared plus a squared. So let me just write out one more thing. So we have 5, let me write it like this, 5 times s over s squared plus 9. Then we have plus, well, what do we really want in the numerator? We want a over s squared plus a squared. A is 9. Sorry, a squared is 9, so a is 3. So I want a 3 here, so I'm going to put a 3 in there. I had a minus 6 though. I can't change the problem, right? So I actually need to, let me put a little more room here. I need to do plus a negative 2 times 3 over s squared plus 9. Okay. Then let's look one more time just to make sure we wrote it in the right form. So s over s squared plus 9, that's going to just be the, sorry, not the hyperbolic cosine, the cosine. And then 3 over s squared plus 9, that is exactly in the form a over s squared plus a squared. That's the Laplace transform of a sine. So we are now ready to take the inverse Laplace transform. This one just becomes 3. Right? So Laplace transform of 1 is 1 over s. We're going backwards. This one is going to be 5 times the cosine of cosine of what? Cosine of at, where a is 3, so cosine 3t. And then we'll have minus 2 times the sine of 3t. Okay, so that one was a bit more complicated, but the main idea is we're going to use partial fractions. I guess I should label this. So it's called partial fractions. To rewrite this rational function as a sum of basically simpler pieces. And then once we do that, we can use this table like we did in previous examples. Okay. You'll notice that most of this process was just algebraic manipulation also. We didn't actually take the inverse Laplace transform till right here. We were just trying to write this in a form where we could recognize this as a Laplace transform of some function. And that's this function here. So in the next lecture, we're going to see how to apply Laplace transforms to solve differential equations.